Welcome everyone. We are on our last lesson about momentum, and today we're going to look at impulse. Not the impulse to do something, not impulse in the English language, where it's like they describe people as being impulsive, they just do things without thinking. This is science impulse, okay? So, why is it that a person in a car is more likely to get hurt in a car accident if they drive into a truck than the person in the truck? This is actually an important question. This is something that affects our lives. We sometimes think about it and we sort of go, maybe the truck exerts a bigger force, car's not as strong. We have all these things. Well, we're going to explain it today. That's what today's lesson's all about. It's all about impulse. When we look at momentum, we have done so much already. So we've looked at the definition, we did the equation, properties, Newton's laws, we did the change in momentum, conservation of momentum was really important, conservation of kinetic energy, and today we're going to look at impulse. So, our key words are net force, you know what net force is, impulse, and change in momentum. Now, out of those three key words, net force isn't new, change in momentum isn't new, impulse is the new one. So we've got to get rid of what we think of in terms of the English language and what we think impulse is, and we're going to go into what science calls impulse, okay? So, we're looking at it in detail now. So, impulse, we're going to look at its definition, okay? And its definition is a little strange because impulse is one of the only things you use at school that doesn't have its own symbol. It's a combination of symbols, which also feels a little weird, but it's okay. Then we're going to look at the equation, which is going to look very similar to you. It's going to look familiar because it's very close to the equation we used when we looked at Newton's second law in terms of momentum. It's related to that. And then, of course, we're going to have to deal with the fact that it's a vector. So impulse is another vector that we need to use. So we're going to have to work out where do we get the direction of impulse from? Because we're going to be looking at net forces, we're going to look at change in momentum, and we're going to have to put all of that together. But it's not as difficult as it seems. Right. So, what is impulse? When we can only get impulse when an object's momentum changes. That means we have to have a force that gets exerted on an object. When a force is exerted on an object, we can say that it's experiencing impulse. But it's not just about the force. It's also about the time it takes. When we looked at conservation of momentum, we had two objects colliding. Impulse is definitely an issue. But even when we looked at change in momentum, just with one object, like a ball being hit by a tennis racket, there's still impulse because there's a force being exerted. In science, we define impulse as being the net force acting on the object multiplied by the time it takes for that force to be exerted, which is quite weird, let's just be honest. So, impulse is defined as the product. Guys, this is very important. Please be careful with this definition. I often get told that impulse is F net and time. It's not just F net and time, it's the product. Product means we need to multiply them together. This also means for me that this net force gives me the direction. The unit of impulse is something new. It's Newton seconds, not Newton per second. So you can't do this and I see it a lot, when it's s to the minus 1, you're telling me I'm dividing by time. But we're not dividing by time, we're multiplying. Please be careful with this one, okay? Because it's an easy one to get wrong because you're not used to having seconds without a minus on it, okay? Impulse is a vector, I've said that already. The direction of the impulse is the same as the direction of the net force. So if my net force is to the right, impulse is to the right. If my net force is east, then it's east. So we have to look at what direction the net force is acting. Now we're going to have to consider Newton's third law again. This is going to become important in this section. So you've got to keep it in the back of your mind. So, how are impulse and momentum related? I've just said to you that impulse is net force times time, okay? So I've just said to you that impulse is F net times time. I'm now asking you to think about the fact that when a force acts on an object, the object's momentum will change. We think back to what we know about Newton's second law in terms of momentum, and we know that F net is change in momentum over change in time. Now we do a little bit of maths, and I'm going to take the time over, and look at that. F net times time is change in momentum. So, the impulse that an object experiences is equal to the change in momentum. Now, right now is why when we did Newton's second law in terms of momentum, I emphasized, and this is really important, that we said that the net force acting on an object is equal to the rate of change of momentum. You have to use the word rate because it means divided by time. Why? Because here I'm telling you that impulse is equal to change in momentum. I'm not defining impulse as being change in momentum. That's still the product of F net times time. I'm telling you that the value, the magnitude of impulse is equal to the object's change in momentum, okay? This gives us, which I've just put there, F net delta T equals delta P. This is the impulse momentum theorem. This is a new one for you, okay? And this says to us that impulse is equal to the change in momentum of an object. They call it the impulse momentum theorem. So sometimes in your questions, they'll say, use the impulse momentum theorem, okay? That means you've got to use the fact that F net delta T, is equal to change in momentum, okay? Be careful, change in momentum, the units. So when I look at change in momentum, these units are kilogram meters per second. Impulses units are Newton seconds. They have the same number value, different units. Okay? Very important here. If I ask for impulse, I want Newton seconds. If I ask for change in momentum, I want kilogram meters per second. All right? It's a big thing, this. So, the direction of impulse is the same as the direction of change in momentum. We've spent lots of time on this. We've had to do it before. The change in momentum's direction is the same as F net's direction. They're all related. They all go together. Impulse is what we consider when people are designing cars. Why do we need to wear seat belts? Why do cars crumple? New cars crumple and the engines drop out. Why do they do that? It's all about impulse. It's all about the change in momentum and trying to make it so that we have a bigger stopping time. Because if we have a bigger stopping time, we'll experience a smaller force, which we are going to deal with, so don't stress. Okay, we're done with this section, so we've done our introduction. We're going to look at how force and time are related for change in momentum and for net force, but we're going to do that after a short break. So I'll see you in a couple of minutes. Welcome back. Let's continue our investigation of impulse. I'm very excited. I love this section. Okay, so what we're going to do is we're going to do a little bit of an investigation with an egg drop. Now, luckily, I don't have to do this in person because it would just get messy. So I'm not going to suggest you do this at home because it's messy and we don't want to waste eggs. Okay, so this is what we've got. We've got a set of conditions with a whole bunch of egg sizes, and what we're going to look is what happens when we drop the egg through a certain distance and it hits the floor. Basically, what we want to try to do in this is see if we can not break the egg when it hits the floor, okay? I have a small egg, which is going to be dropped from 1 meter, and it's going to hit a hard floor. So let's see what happens. Here's my conditions. I've got an egg of 40 grams. It's dropping 1 meter. It's going to go on a hard floor. We're concerned with the zoom in view, the big block. So let's watch what happens. We drop the egg. It's coming. There we go. There we go. And that's exactly what we expected. The egg broke. So let's just have a look at the information that's given to us. Upon impact, the change in velocity was 4.4 meters per second. This took place over 0.000. That's quick. What happens here, and what we have is the equation for Newton's second law in terms of momentum, is it experienced a force of 44 newtons. The egg broke. Okay? So, let's see if we can change the conditions. Let's keep the small egg. Okay, let's change the surface to 1 inch of foam. So that's 2.5 centimeters. So you can't tell on TV anyway because it depends on it's about this big in my hands, I think. Not good with distance. And it's foam. So foam's a little softer, right? So what we expect is the egg should take longer to stop. That's what we expect, so let's see if the egg breaks or not. All right, so here we go. There's my little foam at the bottom. Let's see, oops, no, wrong button. There we go, let's drop the egg. Okay. It says the egg's safe, but it still looked like it broke a little. Let's see what was the same. It still changed by the same velocity. It was still going 4.4. The time is now 10 times longer, okay? So it took longer to stop. It now only experiences a force of 4.4, and the egg was safe. It looked a little broken to me, but it's all right. The longer it took to stop, the smaller the force it experienced. The change in momentum is the same. It still hits the foam at 4.4 meters per second, okay? Let's see if instead of the 1.8, we put it in a foam box, okay? Let's see what happens. Big foam box, so if this breaks, then there's a problem. So let's drop the egg, see what happens. It goes into the foam, absolutely safe. Look at the time. Compared to the 1 inch foam, that's double the time period. it now experiences half the force. So force and time are related. They are inversely proportional to each other because the change in momentum is the same. Let's go and let's use a large egg because we can. Okay, let's drop the large egg from 5 meters and put it on a hard floor. I think we can all make a prediction as to what's going to happen, but let's do it anyway. Okay, so we're going to drop the egg. What you're going to see is you're going to see the egg a little bit on the zoom out view. The zoom in view is just the last meter. So here we go. The egg's dropping. We can see it. And here it comes. It very much splashed. Okay, egg very broken. The velocity, 9,9. It took 0,003 seconds to drop and experienced a force of 198 newtons. It's very broken. It's smashed. It's a mess. Okay? Let's see. So we saw with the small egg that the 1-inch foam prevented it from breaking. Okay? So let's see if that will work with the large egg. So we're going to do it again. Let's see. And there it goes. There it goes. It says the egg is safe. I'm not convinced, but it's all right. What did we do again? We made the time 10 times slower. So this became 10 times smaller. Okay? It took less time, force becomes smaller. Okay? Let's go and do it with the foam. Let's do the foam box. Let's run the trial. Okay? If it was safe on the inch foam, it should be safe on this one. And again, we increased the stopping time. Took a lot longer to stop. Force is much smaller. The longer it takes to stop, the smaller the force it experiences. Okay? Let's see just if this works, if we use the jumbo egg in the foam box. Okay? The jumbo egg is 80 grams, so let's drop the egg. Should be safe. What I need you to see, though, is the large egg and the jumbo egg, when it's dropped from 5.5 meters, still hits the ground at 9,9 meters per second. Doesn't matter about its mass. Its mass determines the force. So this one got 13,2 newtons. The force is bigger that it experiences because its mass is bigger. But it still stops in exactly the same time. That's the important thing to get here. That here, the change in momentum is determined by the mass, not the velocity. How long it takes to stop is dependent on what it falls into. So the longer we can take it to stop, the smaller the force it experiences. And that's what we're looking at with impulse, okay? So let's put this into some words. Why is it useful to express impulse in terms of momentum? If we think about this logically, we've said F net delta t equals change in momentum. Change in momentum is much easier to measure. It's easy to measure the change in velocity of an object. It's easy to see the time. So using change in momentum, we can calculate the force that an object experienced. It's exactly what they do when they look at car accidents. And now they're trying to decide, I'm sure you've seen crime scenes shows and all the rest of it, and they're trying to determine what force the impact was. They can calculate the change in momentum. And they can work out what time it took for the force to happen. That way, they then work backwards and they get the net force that's experienced. And remember, when two objects collide, they both experience the same net force for the same amount of time. Please, Newton's third law can't get thrown out the window in this section, okay? So, during a collision between two objects in an isolated system, both objects experience equal and opposite forces. Why? Newton's third law. Oh, there we go. Newton's third law. Okay, this is what I'm trying to get. So, if I have an object here, and I have an object here, let's call this A, let's call this B. A pushes on B, so this is the force of A on B. B experiences a force on A. Okay, they are both in contact for the same amount of time. Okay, we know that F net, oopsie, no, I'm trying to find it. Okay, we'll just draw it all again. So A, B, we're good with this. Force of A on B, force of B on A. F net, delta T is impulse, okay? Both of these experience the same force, which is F net, for the same amount of time. But one of them has to be negative because we always have to have a positive direction. That can't disappear. So if I make A's direction positive, okay, that means for me that my impulse on A is the negative of the impulse on B. All this means is F net delta T for A is the negative of F net delta T. The only thing that's different is direction. What we may find is that the objects don't have the same change in velocity because their masses are different. That's important to get here. Just because F net and delta T are equal does not mean that they change their velocity by the same amount. Their total momentum will change by the same amount, but not necessarily the velocity. It's mass dependent, okay? So, now, we've looked at it. We've realized that F net delta T can be affected by time. And when we want to make the net force smaller, we have to make Ft bigger. We are going to look at that again in detail. But F net delta T equals change in momentum. And when two objects collide, they experience the same net force in opposite directions. So they have the same impulse, just in opposite directions, which means both objects experience the same change in momentum. I'm saying the same thing over and over again because it's important. Now you're going to take a short break, and you're going to think through what we just did, and then we'll do some problems. I'll see you in a couple of minutes. Welcome back. I hope you had a good break. I hope you got your calculators ready, because now we're going to do some calculations and we're going to do some explanation questions because the two go together. So let's get going. All right. We have a soccer player who kicks a ball with an average force of 21 newtons for 12 seconds. Average force here means F net. We're going to simplify these to only looking at F net. We're not going to try and confuse you and do Newton's second law and do all sorts of weird things in this section, okay? We're going to keep it simple. What we're going to calculate is the impulse provided to the soccer ball, and then we're going to calculate the mass of the soccer ball if the ball's velocity changes from 4 to 2 in the opposite direction, okay? So, first of all, he kicks a ball with an average force of 21 newtons for 12 seconds. We want the impulse provided. I gave you this equation. I can't start here. I'm not looking at change in momentum. Because impulse doesn't have its own symbol, if I'm going to calculate impulse using F net and delta t, I have to write out the word impulse. So we're going to go impulse equals F net delta t. Therefore, I'm now going to put in that I've got 21 newtons for 12 seconds. And we're going to take out our calculators because they're very important to us. So let's use our calculators. We're going to go 21 times 12, and we get 252. 252 newtons. They want the average force provided to the ball. So this is the player, whoopsie. Let's just go back there. Just having moments. This is the player on the ball. Okay, so this is the force that the soccer player, well, the impulse that the soccer player is exerting on the ball. I haven't put the right units. It's Newton seconds. Almost got that wrong. Newton seconds, be careful. Because we're talking about force, it's easy to forget the seconds as well. And remember, it's not per second, it's just seconds. Newton times seconds. We now know what the impulse is. Now they say to us that they want us to calculate the mass of the soccer ball if the ball's velocity changes from 4 meters per second to 2 meters per second in the opposite direction. So first thing we know is I know that F net delta t is 252 Newton seconds. The situation says to me that my soccer ball is going 4 meters towards the player and then is going 2 meters away from the player. What we have to remember is that impulse is a vector. By default, we didn't even think about it. We've actually determined which direction is positive because we got a positive answer at the end, and that answer was the ball, was the player on the ball. So that tells me that this direction with my diagram, so to the right, is positive. That also means for me that the initial velocity was negative. They want mass. We're now going to use the fact that we know that F net delta t equals m delta v. I know F net delta t, it's 252. I don't know the mass, and we're going to be going Vf minus Vi. So 252, here's my mass, and my velocity ended at 2, started at minus 4. That then tells me I'm going to go 252 equal to 6m. At this point, I know I'm going to get a positive answer for mass. I have to get a positive answer for mass. If you do this and you end up with a negative answer, you've made a mistake. Mass is not a vector. Mass is a scalar. Mass can only be positive. So be careful. If you get a negative, go look back. You've done something wrong with your signs. You've done something wrong with direction. Let's put this in the calculator, though, because I know I can't do this in my head. Divided by 6. And we get 42 kilograms. In an exam, If you get an answer of 42 kilograms for a soccer ball, I'm sincerely hoping you're going to go, something's wrong. Soccer ball should not be 42 kilograms. Obviously, something's wrong. There must be something wrong with the information I gave you. It's fine for now, but in the real world, soccer balls are not 42 kilograms. We'd never be able to kick them. But it does explain to me why the soccer player was in contact with the ball for 12 seconds, because it took a lot of effort to get it to move if it's 42 kilograms. And he probably broke his foot in the process. We're not going to worry about that. Your exams are set up so the answers and the values make more sense, so they're more realistic. This is not realistic, okay? But it doesn't matter. You got the concept. Next question. A loaded 10,000 kilogram freight train car rolls at 3 meters per second to the right towards a much smaller 2,000 kilogram freight train car, moving at 4 meters per second in the opposite direction. On colliding, the two cars lock together and continue moving at 1,83 meters per second to the right. Calculate the impulse exerted on each freight train if the collision lasts 0,7 seconds. This is the second question. Calculate the net force on each freight train. They've been really nice in this question in that they've given you all the before information and all the after information, and then they want you to calculate impulse and then F net. Let's start with the first part. We have our 10,000 kilogram freight train car, which is going at 3 meters per second to the right. Then we have our little 2,000 one, which is going at 4 meters per second to the left. They collide, and afterwards they're one object, and they're going at 1,83 meters per second. I'm trying to think if I did give myself info. Now, I need you to be aware of something. When I calculate the impulse on the freight train cars, I know they stick together, but I'm not going to use the combined mass. I either have to look at the 10,000 kilogram car, or I have to look at the 2,000 kilogram car and then work them out separately. I can't add the masses together because I want the force exerted on one and I want the impulse exerted on the other. So we're going to separate it. Now, we need to make a decision as to the positive direction. I'm going to make to the right positive because once they had collided, they kept going right. It just makes sense to me. Let's look at the 10,000 kilogram cart. So this is the 10,000 kilogram cart. We want the impulse that it is experiencing. Actually, I want to write it like this rather. All right, we want impulse. No, that way. Ink, there we go. Impulse, which is F net delta T. Okay, but now we've got to say to ourselves, actually, they didn't give me impulse. They wanted, if you look at the first part of the question, they don't give me delta T. So I can't use impulse as it stands, but what I can do is remember that impulse is m delta v. So I'm using the second part of this equation. The 10,000 kilogram truck, okay. Final velocity was 1,83. Initial velocity was 3. Let's put this in our calculators. Definitely can't do this in my head. All right, so we have 10,000 times 1.83, 3 minus 3, and we get minus 11,700. But remember, We always make it into a positive, so it's 11,700 Newton seconds left. I now need to show you something. They said calculate the impulse experienced on both freight trains. This would be enough. They would both experience this, but I want to show you something because now you're going to go, how did we know to use the 10,000 kilogram truck? You didn't have to use the 10,001. You could have used the 2,000. If we go then and use the 2,000, let's put it in different colors so that it's, okay, so we're going to do the 2,000. All right. We want impulse. All right, and now it's 2,000. Final velocity is 1,83. Its initial velocity was 4, but it was in the opposite direction. So it's -4. Let's just double check that I got that. It is 4, because we don't want to use the wrong values. Let's put that in the calculator. Okay, so we've got 2,000 times 1.83, and that's really +4. Okay, now I get 11,660. And I can hear what you're saying to me. Now you're going, but those aren't the same values. One's 11,700, one's 11,660. Aren't they supposed to be the same? Absolutely, they're supposed to be the same. If you go back to the question and you rework out the final velocity, this 1,83, it's actually 1,833333333. It's 3 recurring. The difference in these two values is the fact that we rounded it off to 2 decimal places. Let me show this to you. So if I go back here, and instead of just 3, instead of 3, I'm just going to put in lots of decimals there. Let's see what happens to the number. Can you see it's getting bigger? So the number gets bigger and bigger and bigger. If I put 33333 in that one, this number will start to get smaller. If I had the exact decimal, those numbers would be exactly the same. Don't worry about it. In an exam, because we know this happens with rounding, you could give me either and it would be accepted. Okay? They are both correct answers based on the rounding. So we're good with that. Don't worry about it. They should be the same. There might be slight differences because we round off our answers. Okay? So, next question. If the collision lasts 0.7 seconds, calculate the net force. There we go. So we want net force on each freight train. If we look at the 10,000, so we're going to start with this one. We want F net delta T equals M delta V. Now we know on the 10,000 kilogram train, it was 11,700, but it was to the left, so this is minus. You can't leave that out. We want F net 0.7 seconds. Definitely need to use our calculators. I'm going to divide by 0.7 on both sides, and we get 1,671. Got to remember that number. 16,000. 16,714. Apparently, I can't write numbers. All right, oopsie, again. There we go, 714. And let's get the decimals, 2 decimal places, 2,9. That would be minus, because I was dividing by a minus. So let's just write this properly. No, wrong one. There we go. So 16,714,29 newtons left. Okay, because it's against it. So I use the 10,000 kilogram truck. I get 11,000. So what should happen is the 2,000 kilogram truck should feel the same force. But what if you'd used the other answer? What if you'd used the answer to the 2,000 kilogram truck? That's fine. If we look at the 2,000 kilogram one, all right? So we know F net delta T equals M delta V. And for the 2,000 kilogram truck, we still know this is 0.7, but we worked this out to be 11,660. All right? So calculator, because definitely can't do this in my head. Divided by 0.7. Oops. And now we get 16,650. 7, oopsie, let's see, 1,4, and this is to the right. Again, it is different to the one we worked out for the 10,000 kilogram truck, but it's okay. It's because of that rounding right at the beginning that we got this. Don't stress about it. Both are correct. In an exam, they will only ask you to work out the force on one and then ask you what's the force on the other, because we're testing, do you understand Newton's third law? So they should experience the same force but in opposite directions, okay? Impulse comes down to Newton's third law. Very important. So now we get to the questions that really get a little hairy for us. You are traveling a bus, it should be in a bus, when an insect traveling in the opposite direction suddenly splatters on the front window. Okay, how does the force the insect exerts on the bus compare to the force exerted by the bus on the insect? That's the first question. How does the change in momentum of the bus compare to the change in momentum of the insect? Second question. Does the bus or the insect experience a greater acceleration? So, first question. How does the force the insect exerts on the bus compare to the force exerted by the bus on the insect? And I can all hear you going, the bus exerts a bigger force on the insect. Nope. Why? Newton's third law. When the insect hits the bus, they exert the same force on each other. It's tiny. The bus doesn't feel it because the bus is so big. The insect, on the other hand, because it's so small, absolutely experiences the force. But the force is the same. They are just in opposite directions. So when they say, how do they compare? The force is equal, but in opposite directions. That's the first one. Please, guys, this is so important for you to get because they ask this often, comes up in lots of types of questions. Then they say, how does the change in momentum compare? If they experience the same force, they must experience the same change in momentum. So remember, impulse is F net delta t equal to change in momentum. They're experiencing the same force for exactly the same amount of time, which means delta p is the same. So change in momentum is equal, but opposite in direction. First two questions, straightforward. Last question, and this is the very important one. Does the bus or insect experience a greater acceleration? Here they want you to remember that acceleration is change in velocity over change in time. We go back to the fact that F net is change in momentum, so I'm going to do this as m delta v over delta t. This is all about mass. We've just agreed that m delta v is the same for both the insect and the bus. The difference is the mass. The bus has a very big mass. This value is very big. This value, the change in velocity, must then be very small because we have to keep it as a constant. I need to keep delta p as a constant. So if m gets bigger, v must get smaller. With the insect, the mass is very, very small. Because its mass is very, very small, this change in velocity must be very big. If change in velocity is very big, acceleration is going to be very big. So the insect has the bigger has the bigger acceleration. Why? It has a small mass, so change in v is bigger, and acceleration is change in v over change in t, therefore it is bigger. And in fact, the reason why the insect splatters is because of its big acceleration. So in a car accident between a truck and a car, which is what we spoke about at the beginning, the people in the car get more damaged, not because they experience a bigger force than the truck, but because there's a bigger acceleration. There's a bigger change in their velocity, and that results in the injuries, okay? Because then there's that fast movement on the seat belts and the airbags, all of which you need to have when you're driving, because they increase the stopping time. And if we make the stopping time bigger, we can experience a smaller force. So you wear your seatbelt, you make sure you got airbags. It's why babies must be in car seats and all of those sort of things. It's a safety thing. Okay, so it's not about the truck exerting a bigger force. It's all about the change in acceleration. It's all about how much their velocity changes. So what have we done? Impulse is the product of net force acting on an object and the time for which it acts. Impulse is equal to the change in momentum of an object. This first one is your definition. This is the impulse momentum theorem. Impulse, momentum theorem. And during a collision, both objects experience the impulse, experience the same impulse. Oh wait, no, I've got it there. Never mind, ignore what I'm doing there. Experience the impulse of the equal magnitude. Ooh, that language is terrible. Experience impulse of equal magnitude, but opposite in direction.